All right, so just a reminder. So last time we defined what a site was. So that was some extra structure on a category, namely a collection of so-called covering families, which satisfied some axioms analogous to what you have if you have a topological space and you declare which collections of open subsets cover which open subsets. We said what it means to be a sheaf on a site, and we gave a bunch of examples, which I kind of owe you proofs of. So in particular, we defined like the fppf and Etale sites associated to a scheme in both big and small versions. And then we finished by saying what a morphism of sites is. And I didn't quite say everything I wanted to say about morphisms of sites, or continuous maps of sites, as we called them last time. So let me remind you about the definition and give a couple examples, and then we'll move on to the topic of today, which is descent. So in particular, this is how we're going to see that a lot of actual kind of familiar objects are actually sheaves on the Etale site. And in particular, I owe you some theorems along the lines of a representable functor is a sheaf on the Etale site, or a quasi-coherent sheaf gives you a sheaf on the Etale site, and that kind of thing. Okay, so let me begin with a brief reminder. So this was a definition of a continuous map of sites. Map of sites. So in particular, we were in the following situation. So we had two sites, C, T1. So C is a category, T1 is a set of a collection of covering families, and D, T2. So then a morphism, or a continuous map, C, T1 to D, T2. Can anyone remind me a definition? What the definition is?
The functor going in the other way that preserves fiber products and the covers.
Yeah, so yeah, exactly right. So it's a functor, which maybe I'll suggestively call F inverse from D to C, such that one, F inverse preserves fiber products, and two, F inverse sends covering families to covering families. Okay, and just a reminder, I'll just remind you verbally. So the main example of this we had from last time was that if you have a map of topological spaces, let's call it F, then the functor going the other way from the category of opens on the target to opens on the source just sends an open to its preimage. And then you had an exercise, which was to check that this actually is a continuous map of sites. Great. So I want to give you a couple more examples. So suppose X is a scheme. Then I claim that there are natural maps of sites from the big ppf site of X. So remember, that was all X schemes, and then covers were collections of flat morphisms, which were jointly surjective. This maps to the big Etale site. So remember there, the category was all X schemes, and covers were collections of Etale morphisms, which were jointly surjective. This maps to the small Etale site of X. So there, objects were Etale X schemes, and morphisms were morphisms over X. And then again, covers were collections of morphisms, which were jointly surjective. And then this maps to the Zariski, sorry, this should be the small Zariski site of X. So this is just the category of open subsets of X with morphisms given by inclusions, and covers are covers. So can anyone tell me what these arrows are? Like how to define these maps?
Just inclusions, like every.
Yeah, exactly. So it's just the natural inclusions going the other way. So for example, if you have a Zariski open of X, that's an Etale X scheme, and that includes into the Etale site. And a Zariski cover is an Etale cover, and a fiber product of Zariski opens is just the same as the intersection, which is the fiber product in the category schemes. So there's just sort of obvious inclusions of categories each way, and you should check, and this is a sort of one-line exercise in all cases, that this is actually a continuous map of sites, that each of these maps is a continuous map of sites. Okay, great. So maybe before moving on to descent, I just want to make a couple remarks on terminology. So first of all, there's several different conventions about what a site is or what a growth unique topology is in the literature. And I just want to remark that what we've been calling a site or a growth unique topology is sometimes called a growth unique pre-topology. So sometimes you'll see a definition of a growth unique topology using objects called sieves, and there's some benefit to doing that, which is just that in our definition of a growth unique topology, we assume the existence of certain fiber products, and strictly speaking, you don't have to assume that. If you use this fancier definition, I just find it difficult to work with, and this will suffice for all the kind of sites that we're working with. So the other term you might see thrown around if you look at literature on this topic is the notion of a topos, which is the category. It's one definition is that it's a category equivalent to the category of sheaves on a site. And there's a sort of more intrinsic characterization, which you can look up if you care about this. And maybe it's worth remarking, I mean, a lot of the things that we're doing in terms of sites, we could in principle express purely in terms of this language of toposes or topoi, depending on what kind of plural you like. And there are benefits to doing that. And if you want to know what they are, you should come to my office hours, which, just a reminder, are Mondays at 10 a.m. But again, it's sort of, I think the sort of geometric picture is a little clearer if we stay with the site. So that's what we're going to do. Okay, are there any questions about that before we move on to talking about descent? All right, if not, let's talk about descent. Okay, so let me, I'm very excited. I don't know if you saw this over here. I put 3 exclamation points by descent because it's maybe one of my favorite topics in all of mathematics. So let me start by motivating the question. So the question for us is, so we've defined all these sites, and we've said what it means to be a sheaf on a site, and so far I haven't actually proven to you that any honest functor is actually a sheaf. So the question is how to check. To check if something is a sheaf, say on the Etale site of X, or on the fppf site of X. And then, I mean, similarly, like, how do you actually construct sheaves? Okay, so I want to give 2 examples. So the main theorem will be, it'll be 2 ways of constructing a sheaf. So one is that if Y is an X scheme, so that just means a scheme equipped with a map to X, then the functor Z maps to Hom over X. ZY is a sheaf on the fppf site of X, and then hence also on the big Etale site, small Etale site, and so on. The Zariski site also, although I think you probably knew already that representable functors were sheaves on the Zariski site. Okay, and then 2, this is one way of producing sheaves, and I promised you this last time that a representable functor is a sheaf. So two, so suppose that F is a quasi-coherent sheaf on X. Then you can take the functor that sends a Z scheme let's say Z with a map X called a map called F to X to the global sections on Z of F star of F. So you pull back your quasi-coherent sheaf and then take its global sections. So this is a sheaf again on the fppf site. And then hence on the Etale site, the big Etale site, and the small Etale site. Great. And this is a sheaf. Let me make a definition. Let's call the associated sheaf on the small Etale site. Let's call it F Etale. So it's given a quasi-coherent sheaf, we can associate to it a sheaf on the Etale site of X. All right, are there any questions about that? And Benjamin asks if fppf is the finest topology for which this holds. So no, there's a notion of a morphism of effective descent, and you could use those to define a topology. I think it's sort of the finest natural topology. So sometimes you'll also see people talking about FPQC instead of fppf. So that's just finite. Sorry, that's faithfully flat and quasi-compact rather than faithfully flat and finite presentation. And arguably that's finer than fppf, but there are somehow set theoretic issues. So I've been eliding all the set theoretic issues underlying everything here because I've been making choices which avoid them. But if you try to use finer topologies like you think about FPQC morphisms, the category of FPQC X schemes, like the collection of objects is not a set, and that causes issues if you want to be really rigorous about things. So it's actually not clear to me that there is a finest topology in the sense that like if you try to make finer and finer topologies, it seems to me like you're inevitably going to reach some situation where you run into set theoretic difficulties. I mean, which can be avoided if you make other choices, but maybe let's not get into it. Does that answer your question, Benjamin? Okay. Sorry for giving such a Weasley answer. I mean, I've been intentionally designing the course to avoid all set theoretic difficulties, and then that means that I don't want to discuss them. Okay, so let me kind of let's try to check what would we have to check to see that these kind of functors are actually sheaves. So Arvind asks, is this not true if it's not quasi-coherent? So this definition of F star, let me remind you, is not just pull back on bare sheaves. It's you pull back the sheaf, you take the inverse image of the sheaf, and then you tensor with OZ. And that's something that'll kind of only make sense if F is quasi-coherent. Right, so even the statement of this part two is kind of only about quasi-coherent sheaves. Excuse me. Does that answer your question, Arvind? Great. Okay, so we're actually going to prove a slightly more general statement. So let's start with part two. So let's start with two, and then we'll deduce actually this statement about representable functors from a statement about quasi-coherent sheaves. So I want to make a definition. So we're in the following situation. So suppose U to X, and maybe you can think U is the disjoint union of some UI, is an FPPF So you have an fppf cover of X. And here are some questions you can ask about it. So suppose F is a quasi-coherent sheaf. So F is in quasi-co, but it's a quasi-coherent sheaf on U. When does it come from a quasi-coherent sheaf on X? Okay, and maybe we can even ask a more precise question. So more precise is, so what extra structure do you need? So what extra structure do you need to descend it? And we'll make that precise in a second, to a quasi-coherent sheaf on X. So when I say come from the quasi-coherent sheaf on X, I mean, when is there a quasi-coherent sheaf F prime on X and an isomorphism between its pullback to U and this sheaf we're given? Okay, and then by this more precise question, I mean, maybe what kind of extra data do we need to associate to this sheaf F to pick such a descent, so to pick a sheaf on X and an isomorphism between its pullback and what we started with. Okay, so that's kind of question one. And then if we think a little bit more categorically, maybe you would also ask the same question, not just about objects, but about morphisms. So given F1 and F2 in quasi-co-X or quasi-co-U, and a morphism between them, so a morphism from F1 to F2, when is sorry, maybe a better way of saying this is, suppose I start with two quasi-coherent sheaves on X, and then I pull them back to U. So I suppose I have a morphism between the pullbacks. So the question is, when does this morphism F come from X? Okay, does anyone have any thoughts on this before I sort of explain the way that Growth and Deek teaches us to think about these questions? Etale.
Is an example to keep in mind X equals spec K and U equals spec of some extension?
Sure, yeah. So if you've seen Galois descent before, that's the sort of situation that Arvind is talking about. So if X is spec K and U is some finite separable extension, then this kind of question is exactly what Galois descent is about. That's a really good example. Yeah, so Sophia says we want its restrictions to the UI to be compatible with intersections. That's exactly right. So maybe one example, so an example to think about is the case where U is a disjoint UI, X is a Zariski cover. Yeah, and this is precisely the motivating example. So in that case, suppose we have a sheaf on U called F. What extra data do we need to get a sheaf on X? So the data we need to get a sheaf on X is, well, we need isomorphisms from F restricted to UI to F restricted to UJ. So these are called gluing data. And then you need a condition on double intersections. Sorry, when I say this, I mean, yeah. Maybe let me write it this way. So we have Fi restricted to UI intersect UJ, and we need an isomorphism between that and Fj restricted to UI intersect UJ, where here Fi is the sheaf given on UI. And then we need a co-cycle condition on triple intersections. Meaning if we go from Fi to Fj and then Fj to Fk, that's the same as going from Fi to Fk. Okay, and then probably you've all seen this before. given data like this, we can glue to get a sheaf on X. Is this familiar to everyone? So maybe you've seen this in the context of vector bundles, for example. Okay, so some people are giving me a thumbs up. If it's not familiar, or if you want to ask questions about it, you absolutely should. Cool. Okay, so this is just the usual statement that if you have a sheaf, it's enough to specify it locally and then to give gluing data. Okay, and then what about morphisms? So a morphism from F to G is the same as morphisms on each of the UI. So morphisms F restricted to UI to G restricted to UI, which commute with the gluing data. Okay, so that's an answer to the second bullet point. Okay, so what we want is a way of imitating this description of gluing data and commuting with gluing data to more general covers, not just Zariski covers. So here's how we're going to do it. So this is a definition, and it's the definition of descent data for quasi-coherent sheaves. So let's suppose U to X is some morphism. Let me call it F. And right now we don't need any assumptions on it. I'm just going to define descent data for an arbitrary morphism. So relative to this map F, so descent data for a quasi-coherent sheaf on U over X is the following. So first of all, it's a sheaf. So it's a sheaf F, a quasi-coherent sheaf on U. Second of all, okay, well now there's these, if we take the fiber product of U with itself, that maps to U in two different ways, the two projections, which I'll call pi 1 and pi 2. Okay, and you're supposed to think of this fiber product as you're taking, if U was an open cover, like a cover by honest open sets, this would be taking double intersections of elements in that cover, right? So this you're supposed to think of as the UI intersect UJs. And what we want is we want gluing data there. And the way we say that is we want an isomorphism, let's call it phi, which is an isomorphism between the pullback of F along pi 1 and the pullback of F along pi 2. Okay, so this is gluing data. And now we need a third condition, which is that this gluing data satisfies the cocycle condition. Okay, and let me introduce a couple more morphisms in order to state that. So if we have take the triple product of U over X, so that maps in three different ways to the double product, right? There's the projection onto the first and second factor, the first and third factor, and the second and third factor. And I'll call these projections pi ij. So pi ij projects onto the ith factor and the jth factor. And one way of saying the cocycle condition is if we pull back this phi along pi 2, 3 and compose with its pullback along pi 1, 2, that's the same as its pullback along pi 1, 3. Okay, so this is descent data for quasi-coherent sheaves. Okay, and the exercise is to check that this agrees with what we had before. If U to X is a Zariski cover. Namely, just a cover by honest open subsets. Okay, so I think this feels a little fancy. One cool thing about it is I think this condition 3 is actually a really slick way of saying what the cocycle condition is. Are there any questions about the definition?
Can you explain this condition 3 again, Daniel?
Yeah, so this is the cocycle condition, right? So what this is saying is that if you, let's go back to the situation where we had a Zariski open cover. So what does this phi do? It says that if we take our sheaf on one of our subsets and our sheaf on another subset, then we have an isomorphism between their restrictions to the intersection of those two subsets, right? So what this cocycle, I'm sorry?
I think you pull back phi, not this.
Yeah, so I'm about to get there. So I was explaining 2, so now let's get to 3. So now what 3 is saying is that if you use that isomorphism to go from subset 1 to subset 2, and then to go from subset 2 to subset 3, so that's something that makes sense on the triple intersection, that's the same as using the isomorphism that goes from subset 1 to subset 3.
I see.
Yeah, and you can kind of see that. So if you look at this, what we've written here, we go from 1 to 2, and then 2 to 3, and it's saying that's the same as going from 1 to 3.
Okay.
Does that make sense? So
Yeah.
over here, maybe one way to say it is that, so commuting with gluing data. So if I give this isomorphism here, the gluing data a name, let me call it phi ij. So what this is saying is that phi jk composed with phi ij is equal to phi ik, and that's the cocycle condition. And Benjamin asks if there's something, if there's some way that this is related to simplicial covers. And sure, I mean, if you take these, if you kind of keep taking these fiber products, that gives you a simplicial scheme. And yeah, I mean, I guess you could phrase this in terms of quasi-coherent sheaves on the simplicial scheme, but for us, because we're in this kind of just one categorical setting, we only have to go this high up in the scheme. Does that answer your question, Benjamin? Okay, and Mencelis, did I answer your question about
Yes, you did.
Okay, great. Okay, so I should also we also asked a question about morphisms, not just about schemes. So I should define for you a morphism of descent data. So given descent data f phi and g c, a morphism between them, f phi to g c, is a morphism of quasi-coherent sheaves. So a map is a map, let's call it H from F to G. So this is a morphism of quasi-coherent sheaves on U, such that the following diagram commutes. So first of all, you can pull back F to U cross U, and you can pull back G to U cross U using pi 1, and then, well, pulling back is a functor, so we can pull back H along that map too. But now we have these two gluing morphisms, right? Phi and psi, which go to the pullbacks along pi 2. Okay, and what we want is this diagram to commute. Okay, so just like before, this is saying that a morphism of descent data is something, it's a morphism of the objects we're trying to descend that commutes with the gluing data. Okay, are there any questions about these definitions?
Sorry, I think I'm getting a little confused. This quasi-coherent sheaf F is literally just a sheaf of modules on U.
So it's a quasi-coherent sheaf of OX modules on U, that's correct. Yeah, so I mean, how does X come into the picture? Well, this pi 1 and pi 2 star are sort of relative to X. They're the projections you get when you take the fiber product of U with itself over X. Does that answer your question, Arvind?
Yeah, thanks. I think I was just confusing it with the sheaf in the growth and loop topology sense.
I see. Yeah, so we're about to get back to that, but yeah, let's so let me kind of state the main theorem about descent data. So the theorem, which is called descent for quasi-coherent sheaves, is that so suppose, I mean, I defined descent data for an arbitrary morphism, but suppose u to x is fppf. So faithfully flat in a finite presentation. And in fact, all you need is faithfully flat and quasi-compact, but I'm avoiding discussing that for this course. So then, let me call this map F. Then pulling back along F induces an equivalence of categories between quasi-coherent sheaves on X and descent data on U over X. Okay, so that's the main theorem. So this theorem maybe doesn't quite make sense because I haven't told you, given a sheaf, how do you get descent data? So can anyone help me with that? So let's make this explicit. So explicit. So given a quasi-coherent sheaf F on X, how do I get descent data?
Just pull it back and pull back its isomorph identity as well.
Yeah, so let's first so we can pull back F. That gives us sheaf and quasi-co of U. And now we need gluing data, right? So now we can take F composed with pi1 star of F, and we want an isomorphism between F composed with pi2. Sorry, the star should be outside the parentheses. Pull back of F. And we want that to satisfy the co-cycle condition. So can anyone tell me how to make this isomorphism? So we want this isomorphism on U cross U over X. Let me draw the diagram, that might help. So we have U cross U. That projects in two ways. You have pi1 and pi2 to U, and then that maps to X via the map F. And so we're pulling back along both of these compositions here, and we want an isomorphism between the two pullbacks. Yeah. So Benjamin remarks that these two maps these two compositions are in fact equal. But yeah, so we're given that because there's a canonical isomorphism just given by pulling back the identity. So here, F composed with pi1 is actually equal as to F composed with pi2. So pulling back the identity is an isomorphism. Okay, great. So the claim is that this functor is an equivalence to categories. Okay, and that's what we're going to spend most of the rest of today proving. And I think this is just absolutely amazing. I mean, and you'll see there's a little bit of a trick in the proof. It's really one of my favorite pieces of mathematics. But before we get into the proof, are there any questions about the statement?
Could you do an example?
Yeah, it's sort of hard to. Yeah, I can give an example. So let me do an example. So maybe I'll give two examples. So example one is if you have let's suppose U is just a Zariski cover. X. So then what's a vector bundle? So one way to specify a vector bundle is, let's just take OUI to the direct sum n, so locally just an honest free sheaf. So this is in QCO UI, right? And if we have the same n, this just gives us a free vector bundle of rank n on U, right? And so what do we need to glue this to a vector bundle on X? So to glue to a vector bundle on X, we need some isomorphisms phi from O UI intersect UJ to the direct sum n to O UI intersect UJ to the direct sum n, such that when we take phi ij, sorry, let me do it this way. When we take phi jk restricted to ui intersect uj intersect uk and compose it with phi ij restricted to this triple intersection, that's the same as phi ik. Okay, so for example, in the case where n is 1, this is just gluing data for a line bundle, right? Is that familiar, Arvind?
Yep.
Yeah, great. Okay, so that's sort of the motivating example we talked about before. So 2, let's suppose that L over K is a separable extension. So maybe let's even make it a Galois extension. With Galois group G. So then we have spec L maps to spec K. This is certainly an Etale cover. So what's descent data? So descent data on this relative to this map, spec L over spec K, is a quasi-coherent sheaf on spec L. So that's also known as a L vector space. With the isomorphisms, with an isomorphism from let me give it a name, an L vector space V, with an isomorphism from pi 1 star V to pi 2 star V, satisfying the cocycle condition. Okay, so let's think for a minute about what that means. So what is spec L times spec L over spec K? So this is spec of L tensor L over K. Can anyone give a different description of this?
Just the Galois group?
Yeah, so it's yeah, the way I would describe it is it's a disjoint union of copies of spec L, which are indexed by automorphisms of L. Yeah, so you're right. It's sort of the Galois group many copies of spec L. So it's not, I guess, yeah, so what I would say is it's a torsor for the Galois group, maybe. I mean, it's, if you'd like, it is canonically split because there's an identity map from L to L. So maybe another way of writing it is the disjoint union over the Galois group of L over K with spec L. All right, so the exercise you should try is convince yourself that that descent data in this setting is the same as Galois descent data. Namely a semi-linear action. All right. Other questions about that? And so my hint is that you're going to have to use this phi in order to build a semi-linear action. Arvin, do you want more examples, or does that sort of satisfy your craving?
That's good. My craving
Yeah.
is satisfied.
It's a little hard to give examples of this, and somehow because you know, after the fact, all examples are just going to be the same as quasi-coherent sheaves on X, right? Okay, so let's start by proving the theorem. So proof of the theorem. And so let me just remind you what the theorem was. So the theorem said that if you have that there's an equivalence of categories between quasi-coherent sheaves on X and descent data on U over X. Okay, so like explicitly, what does that say? So that says that if you have a morphism of descent data, then you get a morphism of sheaves, right? And you get a unique one. So that's full faithfulness of this pullback functor. And then it also says that if you have descent data on U over X, that actually comes from a sheaf on X. So that's essential surjectivity. So what we need to prove is that one, that F star is fully faithful, meaning it induces an isomorphism on Hom sets, and two, F star is essentially surjective. So these are the two ingredients in producing an equivalence of categories. And you'll see actually another way you could try to produce an equivalence of categories is by producing a sort of inverse functor. And you'll see actually that the proof will do that. But it somehow, the structure of the proof maybe more naturally breaks into these two steps. And a good reference, I mean, this is complicated stuff, so a good reference I would suggest looking at if you want to learn more is chapter 6 of neuron models by Bosch, Luke Boehmer, and Reno. And I also mentioned this book on the Discord. Okay, so let's first prove full faithfulness. Okay, so what do we need to prove? Can anyone help me out? So like is there a clean way of saying this? So what do we need to do? We need to show, so suppose we're given two sheaves, F1 and F2, which are quasi-coherent sheaves on X. Then we have a functor from morphisms on X between F1 and F2. And well, what does F star do? It sends this to morphisms on U, our cover, between the pullback of F1 and the pullback of F2, right? So we're not trying to show that this map is fully faithful, right? We're not trying to show that this map is a bijection, because being a map of the descent data is more than that, right? It's you need the morphism to commute with the descent data. So okay, so how do we phrase that? Is there a slick way of phrasing that? Let me maybe move this over, give myself a little bit more room. All right, well, so there are two maps now to Hom on U cross U over X. And these maps go, if you'd like, between maybe let me call it f composed with pi1 star of f1, and f composed with pi1 star of f2. And it doesn't matter whether I use pi1 or pi2 here to pull back, right? So these two maps, I guess, are given by, here we could take pi1 star, and here we could take pi2 star. So maybe a better way of writing, let me actually write this in a slightly different way, which I think will clarify things a bit. Maybe a better way of writing this is we have one map, which is pi1 star, which goes from to Hom u cross u over x of f composed with pi1 star f, then composed with pi1 star f2. And then this map is just the same thing except with pi2 star. Okay, but these two Hom sets are canonically equal, just because they're Homs on the same space, and f composed with pi1 is the same as f composed with pi2. Right? All right, so are you guys cool with this diagram? Does anyone have any questions about it? So Arvind, I think, has given me a thumbs up, but maybe it's about something else. A few people are giving me thumbs up. Cool. Okay, so maybe I'll pause for a second because I think this is kind of a complicated diagram. So okay, so what am I saying? Given a morphism on x, you can pull it back to u. That's fine, and then you can pull it back to u cross u in two different ways. Okay, and so the claim is that given a g in Hom of f star f1, f star f2, so a map between the pullbacks, this is a morphism of descent data. If it goes to the same place, if it maps to the same thing. Under pi1 star and pi2 star. And here I'm using the canonical identification between these two Hom sets. Okay? Okay, so maybe this looks familiar, like maybe this looks like the sheaf condition. Do you guys kind of agree with that? Yeah, okay, so there's always one thumbs up. Cool. Yeah, so so in fact, what I claim is that full faithfulness is the same as the diagram above, being a co-equalizer diagram, or sorry, being an equalizer diagram. Okay, so let's check that. So what does it mean for this to be an equalizer diagram? So it means this is injective, so that's precisely faithfulness. And then fullness means that, well, if you have a map here, which maps to the same thing under these two arrows, that means it's a map of descent data, then it comes from here. So that's surjectivity, that's fullness. All right, so do you agree that that's what we want to show, that this is an equalizer diagram? Okay, so Mencelos agrees. Great. So does anyone have any questions about that? So I'll make this explicit in a second. But does anyone see now why full faithfulness implies that quasi-coherent sheaves? Oh, Benjamin asks, why is the claim true? So the claim is true just by working out it's sort of immediate from the definition. So I'm not going to prove that, but maybe I'll leave it as an exercise. What you need to do is check that mapping to the same thing here is the same as commuting with the gluing data. the gluing data is kind of the pullback of the identity. So it's really it's really just hidden in this equality here. Does that hint at least suggest the answer to your question, Benjamin? Great. Okay. So can anyone tell me, maybe assuming this full faithfulness or assuming this equalizer diagram, why quasi-coherent sheaves give you sheaves on the Etale or the fppf side? We'll go through this again later. I'll actually write it in the notes, but I'm curious if I just wanted to check you guys are following. So let me remind you, so what did it mean to be a sheaf? It meant that some diagram was an equalizer diagram, and that diagram was just what you get when you replace these HOMs with taking global sections of F on X, U, and U cross U. Yeah, so Benjamin, it's the sheaf condition for the single cover U to X, but maybe my question is, what should you take F1 to be and what should you take F2 to be? So suppose I want to prove some sheaf F. Gives me a quasi-coherent sheaf F gives me an honest sheaf on the Etale or fppf side. How do I plug it into this claim about full faithfulness? So the remark is that so Ben has suggested taking F1 to be O, yeah. So if we take F1 to be O and F2 to be some sheaf F, this exactly shows that F Etale or F, for example, or F fppf, so this sheaf we got on the fppf site by just pulling back is a sheaf. And why is that? Well, taking F1 to be O, we get this here is global sections of F on X, this is global sections of F on U, and these are the two maps to the double intersections. Great. All right. So we want to prove that this is an equalizer diagram, but before doing that, we need a lemma. And maybe we have 20 minutes left, so maybe let's take a 2-minute break since we've been going hard. So Benjamin, don't ask, do I need to show this for covering families? So I sort of did a sneaky move here. So I set U here to be the disjoint union of the UI of some UIs. So it's in this setting where I'm allowed to take disjoint unions, it's always enough to work with covering families consisting of one object. Because if I have some random covering family, I can just take its disjoint union, and then I get one object. Does that answer your question, Benjamin? Okay, and Benjamin asks, okay, and this works for infinite covering families. So okay, it slightly depends on your definition. So if you have quasi-compactness, you can always get yourself into a finite covering family situation. Yeah, but in a second, I'm going to kind of omit some reductions. In a second, I'm just going to go to the affine case, and then everything will be very clear. But yeah, you should be careful if you're trying to execute this in sort of non-quasi-compact situations. All right, are there any other questions? All right, let's take a 1-minute break, and then I'll state the lemma. So how are y'all doing?
There's lots of notation.
Yeah, it's a lot of notation. Yeah, so this descent stuff is really hard. You should really just think about gluing, like think about the Zariski situation, and then later on you'll come to think of the Etale situation and the fppf situation and so on as just like them. Okay, so it looks like maybe we won't finish the proof of fppf descent today, but we'll get as far as we can. All right. Any other questions before our 1-minute break ends?
So just on a sort of philosophical question is, we should be viewing a sheaf on a site as something that's like a scheme.
So a scheme gives you an example of a sheaf on let's say the Etale or fppf site. I think not, like, it won't literally be the case that all the examples we think of are representable. Most of them will be. I would think of a sheaf as like on a site as like a sheaf on a space. That's how I would say. Does that answer your question, Arvin?
I would have been happier if you said yes. You should think about it.
Yeah, I somehow don't think so. Like, one way of saying it is, so here's an equivalent definition of a scheme. So a scheme is a sheaf on the Zariski site, which is locally representable. Okay, and you have to work out what it means to be locally representable. But what that's saying is that being a scheme is a genuine condition on a sheaf. It's not like somehow not every scheme is a sheaf. And in fact, in a little bit, I'll make some remark, maybe early next class period on Thursday, about algebraic spaces, which are those are examples of sheaves on the Etale site, which are not representable by schemes, but they're locally representable in the Etale topology. Right. So somehow being a sheaf is genuinely a little bit weaker than being a scheme. Yeah. I think it's not like a sheaf in general doesn't really need to be geometric. Okay, so let's state the lemma. So let me just remind you where we were. So we have this functor between quasi-coherent sheaves on X and descent data on U over X. And we're trying to show that that functor is fully faithful, meaning it induces a bijection between morphisms of quasi-coherent sheaves and morphisms of descent data. Okay, so we're first going to prove what looks like a kind of abstract lemma. So suppose R to S is a faithfully flat ring morphism. So faithfully flat just means it's flat, and the morphism on specs is surjective. And suppose I'm given an R module N. Then there's a following diagram we can write down. So we can take N. This maps to N tensored with S over R, just via the map sending an element N to N tensor 1. And then this maps in two different ways to N tensored with S, tensored with S, where again, all the tensors are taking place over R. And here, what are the maps? The maps are identity on N tensor, identity on S tensor 1, and identity on N tensor 1 tensor identity on S. Okay, and the claim is that this diagram is an equalizer diagram. Okay, so can anyone tell me how this diagram is related to what we're trying to prove? So I claim this is actually a special case of this stuff from before, modulo the fact that I don't assume that R to S is finite presentation.
It's just a local picture, right?
Yeah, so it's local. So it's a little bit more special than that, because here we had two sheaves and here we just have one sheaf. So can you explain this? Or do you see how to specialize to get this picture? Yeah. So this is the case. So this is the case where F1 is O. F2 is the quasi-coherent sheaf associated to N, which people sometimes write N tilde, and then the cover in question. So then U is spec S, and X is spec R, and the morphism here is induced by the map from R to S. Okay, so this is precisely this case, and you should check that it is actually this case, like that these are the maps. That this is like in terms of rings and modules how we write down the maps. Okay, and let me just remind you, what does it mean to be an equalizer diagram? it means that if you go from n, well, it means that this is injective and its image is precisely the subset of this, which maps to the same thing under both of these maps. Okay? Are there any questions about this? Okay, so this is actually not a totally trivial theorem or lemma, and it really uses faithful flatness. So let's actually prove the lemma. So it has two steps. Okay, so the first step is to observe, and this is, I think, like the amazing trick that goes into this proof. So first of all, you observe that without loss of generality, the map R to S splits. Meaning there's a map back like this, so that if you go from R to S and then back, that's the identity on R. Okay, does anyone see how to do this? So this is where we're going to use faithful flatness. Okay, so here's the idea. So the idea is to tensor with S. So okay, so we have R to S, and we can tensor with S, right? So tensoring with S is just the same as pushing out this map along itself. Okay, now I claim this map on the right has a section. Can anyone tell me what it is? So here, this map is one tensor identity S.
It's just multiplication.
Yeah, so this has a section given by multiplication. Okay, so I claim, so the claim is that we can replace R with S and S with S tensor S over R. Okay, can anyone tell me why we can do that?
Because S is faithfully flat, so it's not going to change our exact sequence.
Yeah, so the proof of claim is that we want to check that the sequence n to n tensor S to n tensor S. So here, this is the difference of the two maps above. We want to check this is exact. And then the idea is that it suffices to do this after tensoring with S. So why is this? Because a sequence of R modules is exact if and only if it's exact after tensoring with S.
Sorry, you say that it's the difference of the two maps above. Which maps above?
Sorry, these two maps. So I'm saying being an equalizer diagram is just the same as this sequence being exact. And that's sort of just from the definition, right? So this being this map being injective is the same as this map being injective because they're the same map. And then the image being the stuff here that goes to the same thing under these two maps is just the same as the image being the stuff that goes to 0 under their difference. Are you with me, Arvid?
Yeah, thanks. I just didn't see the.
Yeah. Okay. So the claim was that it's enough to check this after tensoring with S. So can anyone tell me why that is? Like why tensoring with a faithfully flat ring reflects exactness?
Isn't that just a property of tensoring with faithfully flat things.
Yeah, so I'm asking what the proof of that property is. Yeah, so can anyone tell me? Okay, so one direction is easy. So if you have a sequence which is exact and you tensor with a flat module, it stays exact, right? So the other direction. So suppose when we tensor with suppose when we tensor with our ring, the sequence is exact. Then we want to argue that it was exact to begin with. So can anyone tell me why that's true?
Isn't this just definition of faithfully flat, or am I?
Well, it's a definition, but it's not quite the one I gave. The one I gave was that it's flat and surjective on spec. Yeah, that's a definition I prefer maybe because it's something you can actually check. Yeah, so the proof is just that you can check exactness on stocks, right? And when you tensor with something, the stocks are the same. So what you need to do is you need to check that for each point on spec R, the map on stocks is exact. But that's true because we have a surjective map, and you can check upstairs on stocks. Is that clear?
Yes.
Okay, great. Okay, so we've now reduced to this by tensoring with S. We've reduced to the case where we have a section. Okay, so I guess I have eight minutes. So now we're in step 2. So now suppose R to S splits. And I think, by the way, maybe one reason. Let me say what the geometry is. So we have U to X, and we're imagining there's a splitting. So there's a way to go up, so that if you go up and down, you get the identity. So maybe one reason to think that it should be in this case much easier to descend things is that, well, if you have something on U, you can just pull it back along this splitting. So I think that's the geometric picture for this trick. Okay. All right, so let's do it. So suppose we have a splitting, so that's a map like this. Well, first of all, we want to check that n to n tensored over R with S is injective. So maybe I'll call the splitting here I'll call it R. So can anyone tell me why this is the case? So suppose
just compose with, just compose with the splitting and multiply.
Yeah, so you can just have a splitting of this map, just given by the identity on n tensor R. Okay, so that wasn't too bad. So it's injective because it has the splitting itself. Okay, so now we did the injectivity there. Now we want to show exactness in the middle, right? So we want to show exactness over here.
Wait, but is it true that if you take a tensor product and then that splits, then it has to be injective?
Sorry, can you ask that question again, Arvin?
Because it seems you're using a fact that if you tensor and then that map, what am I trying to say? That map admits a splitting, and you're saying that implies that it's injective?
So here I'm using the faithful flatness of the thing I'm tensoring with, right? So I wanted to check this was exact, right? Mm-hmm. Meaning, so exactness on the left here means injectivity, right? So what I did is I tensored with a faithfully flat thing. Tensoring with a faithful flat thing reflects injectivity because it reflects exactness. And then once I did that tensoring, I had a section. So then I'm allowed to just check injectivity after assuming a splitting. Does that answer your question, Arvin?
Yeah, I'm confused because you write it's injective because it has splitting.
Yeah, so I'm saying that this map from n to n tensor S literally has a splitting, right? So let's prove that implies injectivity. So suppose I have something in n that goes to 0 over here. I want to show it was already 0, right? Mm-hmm. Well, but going this way and then back is just the identity. So I have something that goes to 0, it goes back to 0. So the claim is that if you have a map of modules which has a split, that's automatically injected. Does that make sense?
Yeah, cool. Thanks.
Great. Okay, so then exactness in the middle is a little bit trickier, but not too much trickier. So I'm going to define R tilde, which is a map from S tensor S to S. And on pure tensors, it'll just send S1 tensor S2 to S1 times, maybe let me give this map from R to S a name, I'll call it F. So S1 times F of R of S2. So I'm using the splitting here to define a section like this. Okay, and secretly you're supposed to think that in real life, this section is coming from the diagonal map on schemes. All right, so now let's apply this map. Let's apply this map to n tensor S tensor S. So so let's suppose I have something which is in the image of our differential. So let's apply id n tensor R tilde to n tensor S tensor 1 minus n tensor 1 tensor S. So this is what a pure tensor, what the image of a pure tensor under our differential looks like. So this is equal to, just by definition of this map R tilde, this is equal to n tensor S minus n tensor, sorry, F of R of S. Okay, and then if you just use the definition of the tensor product, this is the same as n tensor S minus n times R of S tensor 1. Okay, so what does that tell us? That tells us that if n tensor S tensor 1 minus n tensor 1 tensor S equals 0, so that means you're in the kernel of the differential. Then that tells you that, well, that this last thing equals 0. So we get n tensor S is equal to n times R of S tensor 1. Okay, but this is in the image of our differential. Okay, so that's the proof on pure tensors. So that's the proof on pure tensors. So we proved that if you're in the kernel of the differential, then you're in the image. Okay, and the exercise is to do it in general. Okay, so that I claim completes the proof of the lemma. Maybe since I only have 1 minute, maybe let me make a remark, which is that so given R to S faithfully flat, you can define the Amundsen complex. So that's n to n tensor S to n tensor S, and so on. So in general, you get n tensor S to the tensor R. And here, what are the differentials? The differentials are what you get by taking the alternating sum of where all the maps are the identity on S, except you put a 1 in the ith spot. Okay, and the theorem is that this is always exact. So this is exact. This is exact. Okay, and the proof is more or less the same. So you reduce to the case where you have a section by tensoring with S, and then you use that section to build a null homotopy. Okay, so this is called the Amundsen complex. Okay, and we're out of time, but next time we'll complete the proof of fppf descent. All right, so I'm gonna stop recording, and